Hi, my name is Gürgü Çahay, and for today's video, I would like to present you my second blog, which is about an anti-avalanche protection construction which I developed. Against the backdrop of climate change, traditional rigid barriers are often ineffective. Consequently, we have developed a cascading system designed for the gradual dissipation and absorption of avalanche energy. Mountainous regions face a permanent avalanche risk. A single event can block transport routes, damage buildings and utilities, isolate communities, and create major economic and social losses. The figures shown on this slide illustrate the scale of the problem. They report about 100 fatalities per year in the European Alps and 150 to 220 worldwide, while roughly 6% of the Earth's land area is classified as avalanche prone. Avalanche release is usually caused by several interacting factors: steep terrain, rapid loading by new snow, wind transport, warming or rain, and a weak layer inside the snowpack. Together, these factors increase the load or reduce snow strength until a crack propagates across the slope. Slab avalanches are the most dangerous type because a large bonded layer can release at once and accelerate rapidly. The slide indicates that they account for about 92% of avalanche fatalities, while loose snow events represent a much smaller share. Asphyxia after burial is shown as the leading cause of death, followed by trauma and hypothermia. The first 15 minutes are especially important for survival, which shows why protective structure should reduce impact energy before the avalanche reaches people or infrastructure. Avalanche initiation can be evaluated by comparing the downslope shear stress with the snowpack shear strength. When safety factor approaches or falls below 1, the driving force is equal to or greater than the resistance force and release becomes likely. Conventional metal barriers, snow galleries, and deflection structures are effective in specific conditions, but they can be expensive, rigid, maintenance intensive, or limited in energy dissipation. This creates a need for lighter and more adaptive protection system. The proposed system uses several protection sections placed sequentially along the avalanche channel. Each section absorbs part of the energy, so the snow mass is slowed in stages instead of overloading one barrier. The system includes three cascade sections. Each section combines a rigid arched steel beam, an elastic cable bordered net, suspended rust tires, steel restraining bands, spring damper cables, and rock anchors fixed into the slopes. The arched geometry transfers impact forces toward the anchored slopes. Spring-connected cables reduce peak dynamic loads, while the linked tires act together as an elastic resisting panel that interacts with the moving snow. During impact, the suspended tires penetrate the avalanche body and create resistance through deformation and friction. This scraping and sieving action dissipates energy, while the lighter tire system reduces the initial dead load and can return toward its original position after the event. Each cascade section, the suspended net and tires rotate together through approximately 30 to 45 degrees, while the rigid support retains stationary. The first section receives the highest force, and each following section is intended to handle a smaller residual load. The net height is selected so that the expected avalanche depth does not exceed 1/3 of the net height. Each section follows the channel cross-section, and damper elevations decrease downstream according to local terrain, flow depth, velocity, volume, and discharge. Finite element modeling is used to evaluate von masses, stress, and the response of the spring damper system. Computational fluid dynamics is used to estimate snow flow velocity, pressure, and energy loss through the cascade. In the current numerical model, peak beam stress falls from 480 to 210 megapascals, and cable-related stress falls from 520 to 185 megapascals. These results correspond to predicted reductions of about 56 to 64%, mainly due to the arch geometry and spring damping. The avalanche is presented as a non-Newtonian gradual flow using the Vol-Missal model. Dynamic impact pressure depends strongly on snow density and the square of velocity. So reducing velocity is the most important way to reduce destructive loading. The CFD scenario predicts a reduction in velocity from 38 meters per second to 23.5 after the first section, 11 after the second, and 3.5 after the third. The final value is below the selected 4 meter per second safety threshold, although it is residual velocity rather than absolute zero. Impact is reduced sequentially through damping and friction. Kinetic energy is converted into elastic deformation of the net and springs, together with frictional work generated by the tires and the moving snow mass. Reliability depends on sufficient freeboard adaptation to the channel geometry, the downstream gradient of the dampers, and verified anchor capacity. The design requires a net height of at least 3 times the flow depth and an anchor capacity of at least 1.8 times the maximum calculated load. So the process has 4 stages: initial impact on the arched beam, friction and filtration by the tires, energy absorption by the spring dampers, and final deposition. In the model, the flow falls below the critical velocity and is expected to stop within the cascade zone. Compared with the selected conventional analog, the numerical results predict lower beam stress, lower damper load, much greater velocity reduction, and a safety factor of 2.15 instead of 0.95. These are promising model outputs, not yet experimental proof. The simulations indicate strong structural resistance, effective stress redistribution, and more than 90% reduction in kinetic energy. However, laboratory testing, scaled physical experiments, and field monitoring are still required before full-scale deployment. The preliminary estimate suggests a possible 45 to 55% reduction in capital cost compared with reinforced concrete galleries. Lightweight components, rapid installation, reused tires, and point anchoring may also reduce transport needs, waste, carbon impact, and disturbance to the mountain landscape. The main objectives are longer service life, more reliable load redistribution, lower material and installation costs, and better environmental performance through the reuse of secondary materials. The next step is to verify these benefits experimentally. In conclusion, the Cascade concept offers a flexible and potentially cost-effective approach to avalanche protection. Engineering begins with an idea, but it must end with evidence. Thank you for your attention. I will be glad to answer any questions about the topic in the comment section. Thank you.